Now that we have our return to the stock and our risk premium, we're ready to figure out what the relationship between those two are. Our hypothesized relationship looks like this. We have the return to the stock equal to some intercept term plus the risk premium times beta sub s. So we have the x variable, the risk premium, and the y variable, the return to the stock. At this point we need to draw that relationship, and then we're going to draw the best fitting line through that relationship. But let's look at the relationship first. Easiest way of doing that is just highlighting our two sets of data and going all the way down to 61, row 61. 61 will give us 60 data pairs, and we'll plot a point as the intersection of those pairs. In other words, this last one we're going to draw on an XY. In fact, let me show you what an XY looks like to remind us. So if this is our XY graph right here, yeah, I'm using the one that we're going to be using, by the way, too. So the horizontal line is the x-axis, the vertical line is the y-axis. If we go negative 135 over, because that's x, and negative 128 down, we're going to plot 1 point. And then we're going to do that for all 60 points and see if it looks like there's some sort of a relationship. So to begin with, I'm going to just click the scatter with only markers, that very first option. I'm going to go up into one of the corners of that graph. It doesn't matter which corner, just make sure it's not on top of a word because it will want to adjust that. We just want to go to an empty spot. There's more empty spots on this side, so I'm going to right click and move down to, or choose the move the graph, move chart option. You get a dialog box. Yeah, I've been doing this for a while to get it right. So we're going to say new chart, new sheet. We'll do capital asset pricing model chart. And it will just dump it on its own chart down here with that title. I'm actually going to move it over so that I'm going kind of in the order I created them. I'm going to tap on any one of these, and to begin with I'm going to look at the select data. It's only looking at the one data set that it has, which will have both X and Y, and I'm going to first off move this over a little bit so you can see both the data and the edit. So when I hit edit, you can see that it's saying that A, whatever's in column A, because it goes A2 through A61, are my X variable. Well, that's not even right. Those are my B. It's B that's the X variable. So I'm going to highlight on top of A and type in B, highlight on top of the other A and put B, and down here with the A, or with the Y values, it says that those are the ones in B. Well, that's not true either. Those are in A. So I've got to change those around. A and A. I'm going to say OK. And then I'm going to say OK. Now, having done that, the question is, what kind of a relationship does this look like it is? Now, I mean, it's going to be a linear relationship. Does it look like it's going up this way? Does it look like it's going down this way? If I were trying to draw a line that kind of one straight line through this, the best straight line, which straight line would it be? That's the question I'm trying to answer. By the way, while I'm answering and hypothesizing on that, I'm going to come over here to where it says risk premium. This is the legend. I really don't need a legend, so I'm going to right click it and go down and choose delete. I guess I don't have to go down very far because it's the first thing on there. Now at this point, since you may say, well, I don't know what the best line would be, go on top of one of these points. And it doesn't matter which point, just go on top of one of them, and then right-click it, go down to Add Trend Line, and I wish I could move this out of the way so you could actually see the trend line and everything else, but I guess I can't. So what I'm going to tell it to do is give me not just the line, but display the equation on the chart, display R squared on the chart, and I'm going to say OK. It's going to put it where it wants it. If I click on top of where that thing that it just found, and just, whoops, if I just click and hold, I can move it where I want to, and it's going to work better over here. So I get 1.1176 as a slope coefficient, and notice it's doing y equals mx plus b. So I can understand what it's doing. Oh, it's doing y equals mx plus b. What we're really trying to do is get something that has the capital asset pricing model embedded in it, like this. So here's my y variable, the r sub s, is equal to, since rf doesn't have anything next to it, like a slope or anything, that's got to be the intercept term, and it is. So it's like it's saying y is equal to b plus xm, by the way. Why? Because if we did it y equals mx plus b, you'd understand it easier. But if we completely mix it up, we'll confuse you a little bit longer and you'll think it's magic, when in fact it really isn't. So the RM minus RF is the X, because we said that that was the risk premium. Therefore the beta sub S must be the M, the slope coefficient. Now the beta is also that measure of systematic risk. Anything greater than 1 has more systematic risk than the market. Anything less than 1 has less systematic risk than the market, which means how sensitive is it to changes in the market. Our beta estimate is 1.1176x plus 0.2467. The 0.2467 is the intercept term. And I'm going to talk a little bit about this r squared in just a sec. But for this company, therefore, it has just a little bit more systematic risk than the market. Therefore, we should expect just a little bit more in return than the market. That doesn't mean total risk, by the way. That means systematic risk. Remember that epsilon term I keep talking about and telling you to ignore? Well, the epsilon term is how far these dots are from the line. Some of them are way far away from the line, and others are a lot closer to the line. And it's how far they can vary from the line that epsilon is trying to pick up. And I might add, that has nothing to do with how much you'll get in return, because that is not systematic risk. And it's only systematic risk that's being compensated for in the return. I'm going to go back over the CAPM tab, scroll to the top, and see if there's a way of getting that same kind of output plus a little bit more in just a regression format. When I started this little video tutorial, I said there were two approaches. The first one was the graphing approach, which we've already done. The second one is actually running a regression. And how we run a regression would generally be by going over to data and going to data analysis. Now, if you've been following along so far and you hit data and then data analysis, if you have a data analysis, bully for you. That means somebody's been using your computer and added that portion, that functionality to your Excel. It comes with all Excel programs. Many people never use it, so they don't actually build it in. So if you don't have a data analysis tab right there, go with me really quickly to the file, and we're going to go down to Options. We're going to Add-ins. And the two that I have up here that say Analysis Toolpack or Analysis Toolpack VBA, yours, if you don't have Data Analysis in the Data tab, you don't have these two up in this Active Application Add-ins. In fact, they're down here in Inactive Application Add-ins. So what you would do is click on either one of them, not both, but click on either one of them, and then click Go. As you click Go, this dialog box will pop up, and in your instance they don't have either one of these two added, so just click on them to add them, and then click OK. And as you do that, you're going to end up with Data Analysis in your what's called the ribbon. Now, the problem, I'm going to click on Data Analysis and scroll down to where it says Regression. Then I'm going to hit OK. It wants my Y variable, and I'm going to highlight including the tab, including the label, excuse me. And I'm going to scroll down through 61, and I'm going to then click on the X variable, and I'm going to start on 61 and go up. It doesn't matter which order you do these in, but they should say, in my case it should say A1 through A61, and the second one should say B1 through B61, and I'm going to click on labels because that just tells it that the first row does not have any numbers, it has labels. And then I want to put the output range somewhere on this sheet, so I have to click output range to begin with. For some bizarre reason, it goes up to the Y variable range instead of the output range. I think that's a programming glitch, but it's been there since Excel got started, and that's kind of dumb that they still have a problem with it, but what the heck. I'm going to then tell it where to stick it, which you've always probably wanted to do to your computer, is just tell it where to stick it. So I hit the D1 because that's where I want it to start, and then I'm going to say okie dokie. And it gives me a big honking little output kind of thing. And by the way, it's telling me how many observations there were. Widen that out. And I'm going to point out to you first off that the R squared of 0.161523 is the same one that we get here, because it says 0.1615. It's rounding it to the nearest 4 decimal points on the chart, but it's the same amount. As we look at the sum of squares, the sum of squares is actually partitioned between the explained portion of the sum of squares and the unexplained portion of the sum of squares. So first off, let me tell you what this total does for us. This total, if we divide it by the total number of degrees of freedom, so this one divided by that one, will give us the variance. So I'm going to come up here and say variance. You may remember variance from your statistics class, and I'm going to say that's equal to the sum of squares divided by the degrees of freedom. By the way, in Excel we also could say, what is the variance? And we're looking for the statistic variance. In other words, we're taking a sample. So I'm going to highlight just the R sub S because it's the risk to the shareholder I'm interested in, not the risk to the risk premium. That's kind of weird. So I'm not even going to do that one. And then I'm going to just hit enter, and you'll notice that I get the exact same answer, because the formula for variance is you'd take the difference between the average and each individual number, and you'd square it, you'd sum all those up, and divide by n minus 1. Well, there is the numerator portion, each number divided by the mean squared and added to all of the other ones would be 129.0608. And you may say, how is that possible with 78 being the first one? That's not 78. That's 0.7878. That's how it can sum to just something small like 129. Then as we divide that by n, which is 60, minus 1, gives us 59. Ooh. So we take the sum of squares and divide by number of degrees of freedom. We get the variance, and that's really all we're doing here. But as I've already mentioned, we can actually split this variance into the stuff that we can explain through the regression and the stuff we can't explain through the regression. Having looked at the amount that we can explain versus the amount we can't explain, if I look at what proportion of the total can I explain, let's see. Let me go to an empty place here and say equal, what proportion of the total variance, the total risk, can I explain of the total amount of risk? So we're looking at explained portion as a proportion of the total. I end up with 0.16, which is 16.1523%. Oh wait, that's the r squared. Why? Because that's actually the formula for r squared. This one, the explained portion of the sum of squares over the total sum of squares. What's interesting about this from a capital asset pricing model framework by itself. I've already said that this is really the variance, and from an investment framework, variance is a measure of total risk. What risk is there to my return? We're now taking that apart and saying how much of that is explained by this model. Well, the model's only picking up systematic risk. It says that's the only part that's relevant because that's what the capital asset pricing model says. Therefore, what this is really telling me is what proportion of the total risk is systematic. Now, mind you, r squared does not generally measure that, but in a capital asset pricing model framework, it does measure how much of the total risk of owning this stock is systematic. So we can say that, let me change this and write it, otherwise people go, what, was that important? I'm in a coma right now. So 16.515% of total risk of owning this stock is systematic, meaning I can't get rid of it, which means that the rest of it, by the way, if you want to know what the rest of it is, that would be 100% minus 16.15%. Of total risk is diversifiable. And therefore not compensated if you choose to take it on. In other words, if you're buying this stock and holding it by itself, 83.85% of the total risk that you're going to be exposed to is completely unnecessary. If we bought this stock and a whole bunch of others, then as some of those stocks go down, our stock would have a random uptick off of that straight line. And sometimes when the other stocks have an uptick, ours would have a downtick, and therefore they'd kind of balance one another out, and we wouldn't have as much total risk. It's only the systematic portion that we need to worry about. And this one that means only 16.15% of all the risk that we have in owning this stock is actually being compensated for. How do we measure that? We measure it with beta. Now, just so you can see where the beta is on this output, it's right here. I'm going to make it red and all of that jazz. So how do I know what the return should be? Well, the return to the shareholder should be equal to, and that's what R sub S is, that's the what return should I be expecting would be the risk-free rate plus a risk premium times beta. So I'm going to take my actual risk-free rate, and the reason I'm taking the actual rather than the intercept is the intercept is estimating that it would be 24%, and that's nowhere near where interest rates are right now. I will point out, however, before you say, boy, that's way off, there's so much statistical noise going on here that the p-value is 0.18, which is way too high to be statistically significant. And so I'm going to go over to my risk-free rate and grab the current number divided by 100. I'm going to add to that a risk premium. Now, the way most of these analysts would end up plugging in a risk premium is they would say, what is the risk premium usually? Meaning over a very long period of time, what is it? I'm going to say it's 6%. So I type in 6% times beta. And as soon as I do that, I actually have a formula that is the same as the formula that I have for the capital asset pricing model. I have my risk-free rate plus the risk premium, which over the long run averages somewhere around 6 or 7, maybe as high as 8%, could be as low as 4 or 5%. And so I'm going somewhere in the middle there with a 6% rate. And I'm multiplying it by the company's beta, and I end up with having to pay my shareholders 10.23% return for their investment. That would be my return, or my required return to the shareholder. What the regression formula gives me that the chart doesn't is whether or not this appears to be statistically significant. A couple of places to look and you'll get the exact same answer in this particular case. You always get the same answer. Are these two areas, significant F and p-value to risk premium. Both of these, because this only has one x variable and one y variable, these p-values or probability values will be the same number. And in fact, this f value is taken from an f distribution, and it's based on this number, the mean squared error, divided by this mean squared error. So we're saying how much of it has been explained, how much of it hasn't been explained, and is the explained portion significantly higher than the unexplained portion. So we're just taking this 20.84629 divided by how many x variables we had. In this case it's 1. So some number divided by 1 gives you just the number. In the case of the error term, what's the sum of the squared errors? Well, that's all the rest of the sum of squares divided by all the rest of the degrees of freedom. So 108 divided by 58 gives me 1.85. Then to figure out whether we have more explained than unexplained, we actually just say equal. You don't have to do this, it's already doing it, so don't follow along on this point. Equal my mean squared error, or mean squared regression, divided by my mean squared error. And you'll notice that that number is exactly the same because that's how it's calculating it. Then this significance f, you can't really tell what it's doing, but it's actually saying what is the f distribution given this number, and degrees of freedom 1 being that, degrees of freedom 2 being that, and we get the same number. Just showing you that that's where they're coming from. Just to show you where this number is coming from, by the way, what we're doing here is we're saying this is my best estimate of the slope. This is the standard, sort of like the standard deviation of that slope. If we're hypothesizing that there is no relationship, then this coefficient would be 0 if there weren't actually no relationship, and so we want to see how far away this is from 0. This is actually just doing something that you may vaguely remember doing as a t-test. You'd say some number divided minus the hypothesized number, in this case that would be 0, divided by the standard error or the standard deviation. It's like finding the number of standard deviations you are from the mean, and that's really kind of what we're doing here. So we're saying this minus 0, which is what we're hypothesizing, that there is no relationship actually, and then we divide it by the standard deviation to get a t-statistic. So I'm going to say equal, I'm going to put the parenthesis even though it's really not needed. I'm going to say this number minus 0, that's the hypothesized number, which is just going to be that first number anyway because you subtract 0, it's the same thing. So I'm going to divide that by the standard deviation, and I get 3.342609. Okay, so far so good. Now I want to know what is the probability of being that far out in a t-distribution. So I'm going to say equal t-dist x degrees of freedom. We're looking at the error degrees of freedom, and number of tails. This one has 2 tails because it could be a little too high or it could be a little too low. So I'm going to say 2. And I'm going to close my parenthesis, and yes, I got the exact same percent. But just to show you that these two are actually very closely related, I've already shown you where this number comes from. I'm going to show you again that we could have gotten it. And this only works because we only have one x and one y, by the way. It doesn't generally work for all different types of regression. But if we take this number right here and square it, we get the same number. And all we're doing is taking my t value and squaring it. Probably more information than you really wanted to know. But if we're estimating the beta, which is what we're doing here, this is giving me a lot more information. This p-value right here and this significant f value, again, these numbers should be less than 0.05. If they are, then chances are that didn't happen randomly and there is something going on. In other words, the capital asset pricing model has some value as in estimating the return to the market. Having gone through all of this, one last thing that we have to do is see how close we are with the 1.117 to the beta estimates of others online. So I'm going to pop back to the internet, and this time I'm going back again to financeyahoo.com. I guess I could just hit enter. And I'm going to type back in RCKY, or since I have it here, and quite often it will remember some of the last ones I did, but I'm going to just retype it. Or you can just click that link and it will take you to the same page, this one. And I'm going to choose from this page key statistics. And on those key statistics, I'm actually going to scroll down to here, and they are estimating 1.25, which is kind of close. It's in the ballpark of my 1.11 or 1.12. Kind of close. They're a little off from me, and I'm not saying mine's better or theirs is better, but I'm kind of close, or they're kind of close, depends on how you want to look at it. And at this point I'm going to look at the second group. It's not just Yahoo who can take a look at this. We can actually go to www.google.com/finance. You notice I've actually gone there before too. And I'm going to click down here and type in RCKY. By the way, with this one you can type in Rocky Brands if you want to, and it will find it either with the name or the ticker symbol. This one we don't have to go anywhere. We can look at it right here, and they're estimating 1.12. And I'm going to point out to you really quickly that if I drop mine, round to the nearest 2 decimal points, I get exactly the same thing that Google did. Just saying, Google and I are in agreement. One last place to look is MSN Money. I can never remember how to get here, so I have to go MSN.com, and then I actually have to choose money, type in my ticker symbol RCKY, and scroll down here, and under the financial highlights I'll find Beta, and they also are estimating 1.12, which is exactly what I'm estimating, and so we're all right. Hopefully we're all right together. The one thing that this doesn't tell me is, therefore, how risky is this to hold by itself. The R-squared tells me that. The lower that number, the more risk I'm actually taking on and not being compensated. It also doesn't tell me whether this regression is statistically significant. So hopefully this is helpful. Hopefully you can do this with your company. This is the end of this particular lecture on applying risk and return to my company.